To understand a molecule's chemical behavior, it's necessary to know its connectivity, specifically which atoms are bonded together and by what types of bonds, right? Like single, double, or triple bonds. It's also useful to know which valence electrons participate in bonding and which don't. Lewis dot structures, are sometimes called Lewis structures, are a convenient way to convey this information. So I want to review some of the basics of Lewis structures. So the first thing is that Lewis structures take into account only the valence electrons. So we're only looking at valence electrons. And then bonding and non-bonding electrons are really clearly shown. Single bonds represent the sharing of 2 electrons. Double bonds represent the sharing of 4 electrons. And then triple bonds represent the sharing of 6 electrons. So each line represents a shared pair or a bonding pair of electrons. Non-bonding electrons are indicated by the dots and are usually paired. And those are, of course, we talked about in the previous screencast, are called lone pairs. Now, non-bonding electrons that are represented by an unpaired single dot. So if you have an unpaired single dot, in the species that they occur, they're called radicals. Okay. So atoms in Lewis structures obey the duet and octet rule. The shared electrons of the covalent bond count as the valence electrons of each atom involved in the bond, right? So the atoms tend to form covalent bonds to achieve that full valence shell. And so let's talk a little bit more about the steps for drawing Lewis structures. So the first thing you want to do, and I have this written out here for you, is you want to count the total number of valence electrons in the molecule. Now, remember, you figure out the valence electrons by looking at the group on the periodic table. Right? And then you need to write the skeleton of the molecule showing only the atoms and the single bonds required to hold them together. When you do this, generally, you want to put the most electronegative atom in the center or the interior, right? And that's never hydrogen. Hydrogen's always going to go on the exterior because it can only form one bond. You're going to subtract 2 electrons from the total that you calculated in step 1 for each single covalent bond, and then you're going to distribute the remaining electrons as lone pairs. Now, if there's an atom with less than a filled valence shell, convert the lone pairs from neighboring atoms into bonding pairs of electrons, creating double or triple bonds. Now, I want to review electronegativity just for a second, and particularly the trends, since we have to pick out the least electronegative. I want to remind you that electronegativity increases as we go across the periodic table that way and up the periodic table this way. We're mostly going to ignore the noble gases, so fluorine's the most electronegative. And so when we do these Lewis structures, we want to put the least electronegative in the center. So let's do an example. Okay, we are going to draw a Lewis structure of an ion. It's an anion because it has that negative charge of HCO2. And this goes ahead and tells you it's where the carbon's the central atom. So let's start following our steps. So our first step here is that we are going to calculate the valence electrons. And so I can't switch to a periodic table, but I hope that you are following along and looking at your periodic table. When we have a hydrogen, it's got 1 valence electron. If we've got a carbon, it has 4 valence electrons. Oxygen has there are 2 oxygen atoms. And so because of this, each oxygen has a valence electron of 6. And so that's where you end up with 12 there. And then there's a negative charge. And if you have a negative charge, you need to add 1 valence electron to that. So when we look at this and add this up, that gives us 18. So we have 18 valence electrons. And I kind of view that as our bank. Now, what we're going to do is we're going to put the carbon in the center, and we're going to attach the hydrogens and the oxygens. Now, when we do that, we now need to subtract out the number of electrons. And so we've used 2, 4, 6 electrons for those double bonds. So we're going to come here, we're going to say, okay, minus 6, and that gives us 12 valence electrons. So the next thing we need to do is we need to put lone pairs around each of the atoms. When we do this, we come here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've used up our 12. Now remember, hydrogen's happy with a duet, but the problem is that this carbon doesn't have 8 electrons in its valence shell. It only has 2, 4, 6. So what we're going to do is we're going to convert a lone pair to a double bond. And so I'm going to move that lone pair down and convert it to a double bond. And so what it's going to look like then is we'll have a carbon atom in the central, we'll have a double bond here with the oxygen, and then we'll have 4 lone pairs electrons, then we'll have an oxygen here, and then we'll have a hydrogen here. And when there's a negative charge, a lot of times what you're going to see are brackets and a negative next to it. Not all the time, but a lot of times you will see that. So this is how we draw the Lewis structure. So let's talk about some exceptions to these rules. And 2 of the exceptions that you're going to see is that not all atoms have a complete valence shell and are short of an octet. Really good examples of this are boron. If you've got a carbon with a positive charge, a lot of times that's called a carbocation, right? So it's a cation, but it's the positive charges on the carbon. Aluminum sometimes lacks an octet. And this just occurs when there is not enough valence electrons available to achieve that complete octet. And so, right, they tend to be completely happy. The other thing that you can see, the other exception, is you can have an expanded octet. Right? And this can occur with elements in the 3rd row and beyond. Right? And so they can exceed that octet. Now, atoms in the 2nd row of the periodic table are forbidden to exceed the octet. And that's really important because that's where carbon is. So atoms in the 2nd row are forbidden to exceed the octet, okay? And so a really good example of this is this molecule. It's thionyl chloride, right? And so we see an expanded octet here where we got 2, 4, 6, 8, 10 electrons on that sulfur. Generally, what you're going to see is if you have leftover electrons, then put them on the central atom for small molecules, right? So that's a small molecule. We're going to put it on the central atom. But again, you're not going to see that with carbon. Carbon's not going to have an expanded octet. It's a 2nd row element, okay? Now, I love strategies that and patterns. So if you learn a few patterns, and then it makes drawing Lewis structures very quick, okay? So this table shows the common numbers of covalent bonds and lone pairs for uncharged atoms. So if you have an uncharged atom, right, and it's a hydrogen atom, it's going to make one bond, okay? Then if you have a carbon, right, it can make 4 bonds, and so those can look very different ways. It can be 4 single bonds, it can be a double bond and 2 single bonds, a triple bond and a single bond, or 2 double bonds. If you have nitrogen, right, an uncharged nitrogen has a lone pair, can have 3 single bonds, 2 double bonds and a single bond, or a triple bond. Oxygen is going to have 2 bonds and 2 lone pairs. It can look like this. The halogens are going to have 6 lone electrons or 3 lone pairs and a single bond like this. And of course, then we've got your noble gases, which we're not really going to worry about. Later, you're going to learn that these are the number of bonds and lone pairs for atoms that bear no formal charge. And so again, if we're uncharged, this just makes completing Lewis structures fairly quick. So I want to show you an example of this. So we're going to complete the Lewis structure for the compound whose skeletal structure is shown here, and assume that all the atoms are uncharged. And so here's what you need to do. You need to determine the atoms that have an octet and those that don't. So, for example, I'm going to take red and we're going to highlight the ones that don't. So when we look at this, right, this oxygen only has 2 bonds. It doesn't have any lone pairs yet. This carbon here only has 3 bonds. 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 Now the other carbon next to it to the left, that's got 4 bonds, so we don't have to worry about it. So that's got 4 bonds, that's got 4 bonds, that's got 4 bonds, but this carbon here only has 2 bonds. And then we have a nitrogen here that only has 1 bond. So those are ones where their octets aren't full. And so if you were asked to complete the Lewis structure, what you would do is you would need to go in and either place bonds or lone pairs. So think about how many bonds and lone pairs are typical for each element. So I'm going to start with nitrogen, and I know that nitrogen needs a triple bond and a lone pair, and then that satisfies this carbon's octet because it has 2, 4, 6, 8. This is fine, this is fine. Now I'm going to come here and work on this ring. I know that oxygen needs to be uncharged, needs 2 bonds and 2 lone pairs, and so I can go ahead and fix oxygen there. I can put a double bond here, and now this has an octet, that carbon, because there's 2, 4, 6, 8. And this carbon has an octet because there's 2, 4, 6, 8. This carbon is still lacking an octet, and this carbon is lacking an octet. And so I can draw a line right like that. And now, without really any lengthy calculations, because these atoms are uncharged, and I understand the pattern that molecules that are common atoms that we're going to use take, I can fill everything in. So let's talk about what happens when we have an atom that has a charge. So I want to talk to you a little bit about formal charge. Sometimes we can have more than one Lewis structure for a molecule, and it's helpful to determine the formal charge of each atom on that Lewis structure. So I want to show you an example. Right, so this was the Lewis structure that we looked at before. Okay, and we know there's an overall, and I'm just going to do a half bracket here. Well, let me do a full bracket. there's an overall -1 charge there. Okay. And so we can figure out the formal charge of each atom. So basically what this is saying is, hey, look, we know overall there's a -1 charge, but we want to see if this atom has a -1 charge, or this one, or this one, or this one. Okay. And so to do that, we would calculate the formal charge. Now, if you go out to the YouTubes or the interwebs or the Googles, and you look for formal charge calculations, there's a variety of formulas that you can use and several ways to do this. And you are more than welcome to use any of those. There's more than one way to solve a problem. This is the one that I think is the easiest, and so that's why I use it. So we take the valence electrons, right, and we subtract the lone electrons and the number of bonds. Okay, so we're going to add the lone electrons and the number of bonds, and we're going to subtract that from the valence electrons. So, for example, I want us to do that for this oxygen right here. Okay, when we look at this, for the formal charge here, oxygen has 6 valence electrons. We're going to subtract the number of lone electrons. There are 4 lone electrons there because there are 2 lone pairs. And then there's a double bond, so that means there's 2 bonds. And that gives us 0, and that's the formal charge on that molecule, or that atom. Then we're going to come here, and we see carbon. Carbon has 4 valence electrons. We need to subtract, there are no lone pairs, plus 4 bonds, and that gives us 0. Then we're going to come here, and we're going to look at that oxygen, and we're going to see there's 6 valence electrons minus 6 lone pairs plus 1. And so that's 6 minus 7. That gives us -1. And then on this hydrogen, right, hydrogen has, and I'll do that in a different color. There's hydrogen. Hydrogen has 1 lone pair minus, 1 valence electron minus no lone pairs and 1 bond. And that gives us 0 as well. So that tells us that negative charge density is there on the oxygen. That oxygen has a formal charge of -1. Now, another thing that you can see when you're doing Lewis structures is isomers. So sometimes more than one arrangement of atoms is possible for a given structure or a given molecular formula. So isomers occur when there's more than one arrangement of atoms possible for a given molecular formula. And so when these two molecules are isomers. Now, so isomers then are different molecules with the same molecular formula. And there are a lot of different flavors of isomers, and we're going to dig into that later in the course. But I want to show you an example here. We have ethanol here, and we have dimethyl ether. And what you're going to see is that both of these have the same molecular formula. It's C2H6O, and that means these are isomers of each other. And more specifically, we call these constitutional isomers. All right. So that ends our Lewis structure screencast. In the next screencast, we are going to look at what do you do when you have more than one way to draw a Lewis structure? How do you decide what the best Lewis structure is?